Good day, everyone. Standing before you is Shihlobo Matabe, and I am the president of Bright Star Christian High School Science Club. Here at Bright Star, we believe in excellence, discipline, and strong Christian values. We don't only focus on theory, we make our learning practical. One of the things that makes our school stand out is our well-furnished science laboratory, where learners get hands-on experience through natural science practicals and real experience. We also focus on concepts such as biology, chemistry, physics, and also other things, and also understanding the world through scientific methods. At Bright Star, we are raising future leaders, future scientists, and innovators who will impact the world. Thank you. Good day, everyone. My name is Shihlobo Matabe, and I'm with my group members here, Cloud Shivamu and Bukonamba. Today we are going to test for the presence of starch in different food samples. Here we have a raw cooked potato. Here we have a cucumber. Here we have one biscuit, a potato, and some bread, and also a mango. The materials that we have with us today is the iodine solution, our food samples on top of petri dishes, a knife, a dropper, and a cutting board. Firstly, we are going to use the iodine solution and the dropper, using the dropper to drop the iodine solution on top of the food samples. We are then going to add about 2 drops of iodine solution onto the different food samples. This is the well-cooked potato. This is a cucumber, 2 drops. This is a potato that is not cooked. This is brown bread. And this is a mango. And this is a biscuit. For the observation, if the food sample stays yellow-brown, the test is negative for starch. If the food sample turns blue-black, the test is positive for starch. So here, for the observation, we are going to notice that this food has turned into black-blue, and the cucumber has not changed its color, or it has changed a bit, but the color is not blue, which means that there's absence for starch. Here we have a potato which has turned black, which means that there's presence of starch. And here we have our brown bread. The color has turned into black-blue, which means that there's presence of starch. And here our mango has not changed color, or it has a bit of color change, but then it does not contain starch. Here we have our biscuit, which has changed color into dark blue, which means that there's presence of starch. So in conclusion, we are going to say that if the food sample stays yellow-brown, which means that there's absence of starch, and if the food sample turns blue-black, which means that there's presence of starch. Thank you.
You all, standing before you is Shaka Kando, and I am a member of Bright Star High School Science Club. Today we're going to be testing if certain household substances are acids or bases. So, acids usually have a sour taste and have a pH value that is below 7, and bases have a bitter taste and have a pH value that is above 7. The lower the number, the stronger the acid, and the higher the number, the weaker the stronger the base. And if the value is 7, that means that the substance is neutral. So to test if certain household substances are acids or bases, we're going to use we can use indicators or litmus paper. We have several indicators. We have litmus paper, phenolphthalein, or universal indicators. Each one of these allows you to test if certain household substances are acids or bases. But I decided to use the universal indicator because it is the most reliable. It allows me to test if certain household substances are neutrals and acids or bases, and it doesn't have any limitations. Unlike with litmus paper, sometimes I can only test if a substance is a base or if it's an acid. So this is going to be the first thing we do. So this is our first test tube. The sample in here is so we're going to check if it is, to test if it is an acid or base. We're going to pour 2 drops of our universal indicator. After we do that, we'll have to shake it. Now we'll grab our pH scale and check. The color of this is a dark orange, meaning that it has a pH value of 2 or 3. Our second sample into this beaker so we can transfer it over to our test tube. So our second sample is cooking oil. So we want to test if it's an acid or base. So we pour 2 drops of our universal indicator in here, and then we'll shake it. If we grab our pH scale, it has the color of this is orange. This is orange, so which means it is acidic, and it has a pH value of 3. So our next sample is soap. We're going to put into our third test tube so we can test if it's an acid or base. Test tube, and we're going to pour 2 drops of phenolphthalein in this. The substance in here is soap, and want to check if it is an acid or base. So we'll shake it and look at the solution. The color has changed to a dark blue, meaning that it is a base, and it has a value of 10. So check if salt water is an acid or base. So we'll pour our salt. We'll pour our salt in here, then pour some water in it. So we'll shake the salt and dissolve into the water. And after we'll pour our sample into this test tube. So now we have salt water in here, and we'll grab some our universal indicator and pour 2 drops of it into this test tube. And now we'll shake it to check. Now we grab our pH value and see the color has changed to a dark blue, meaning that this is a base, and it has a pH value of 10. So we want to check if sunlight is an acid or a base. So we'll pour a bit of it into this. So we'll grab our universal indicator and pour 2 drops in here. After we do that, we'll shake it so it can mix. We'll grab our pH value and check the color. The color is yellow, meaning that it has a value of 5, meaning that this is an acid. Our last this is our last sample, which is vinegar. So we want to check if it is an acid or base. We'll grab our universal indicator and we're going to pour 2 drops of it into this. Then we'll shake it so it can mix. We'll grab our pH value and check. The color is orange, meaning that it has a value of 3, which means that this is an acid. Okay, so our final sample, which is water. So we pour a bit of water into this and grab our universal indicator and pour 2 drops in here. Then we shake it. So the color is more a cyan, which means that this is a neutral and has a pH value of 7. So in conclusion, so I have tested most of some basic household substances. So these are the results. Coke is an acid. Cooking oil is also an acid. This is our soup, which is a base. This is our sunlight, which is an acid. This which is also an acid, and our last example, which is water, it is a neutral.
The respected teacher and my fellow learners. Standing before you is Bukola Malebe, a grade 9 learner from Bright Star Christian High School and a member of the Science Club. I'm here with my group members, Dono Maluleka, Kifo Mabasa, and Sabo Chaba, and we'll be preparing an acid and base indicator using a hibiscus flower. It is a pleasure to have the opportunity to speak to you about a fundamental concept in chemistry, acids and base and their indicators. These 2 types of substances play a vital role not only in scientific study but also in our everyday lives. From the food we eat to the cleaning products we use, they are constantly at work around us. Firstly, I would like to give a brief background on what acids and bases are and what indicators are. An acid is a substance that donates hydrogen ion, increasing the concentration of hydrogen ion in a solution, and a base is a substance that accepts hydrogen ion, decreasing the concentration of hydrogen ion in a solution. And our indicators can be defined as substances that change color in response to the change of pH value. So some of the materials or tools that we will be using to make our own hibiscus flower indicator are: we have our hibiscus flowers, our measuring cylinder, our funnel, our beaker, wash bottles, and our droppers. We'll also need a stirring rod, our test tubes, our conical flask, our spirit burner stander, our solution, which is hydrochloric acid, our spirit burner and spirit, including our matches, and some of the other solutions which we can say we can have our acetic acid and ammonium hydroxide solution. So firstly, we'll need about 10 to 15 grams of hibiscus flower, but we'll be placing them into our beaker. And then we'll measure our water using our measuring cylinder. So we are going to measure our distilled water up to 100 milliliters. Then we're going to pour it into our pancake. Now we're going to make our own fire using our spirit pan, whereby we're going to pour our spirit into our spirit burner. And we're going to light up the fire. And then we're going to place it under our spirit burner stand. Then we're going to put our solution on top of the spirit burner stand, which we will call or name it as our hot plate, and let it burn for about 5 minutes. Then we can extract the color of the hibiscus flower to make our own cake. As our solution is burning up, I was extracting our color. We're going to be stirring our solution using a stirring board to make sure that we get the color from each and every flower that we have put into our cake. And as our solution is burning, we're going to pour some of our solutions into these test tubes. We have test tube 2, 3, and 1. Has been done extracting the color from our hibiscus flower, so I'm going to use our tools to remove the beaker from the hot plate to avoid burning, because some of the safety measures that we have to follow is wearing our gloves, our goggles, and using visible tools to remove our beaker from the hot plate to avoid burning our hand. So we are going to brown our fire. And then we're going to let our solution cool down before we decant it into our container. Now that our solution has cooled down, we are going to decant it into our conical flask, and we're going to use a funnel to avoid spilling everything. And then this is our hibiscus flower indicator that my group members and I have prepared. Now we're going to test and see if it's really going to work using some of the solutions that we have, which is ammonium hydroxide, acetic acid, and our hydrochloric acid. So we're going to have our test tube 1, test tube 2, and test tube 3. So I'm going to pour a little bit of our solution into each test tube. Now we're going to pour our ammonium hydroxide into our test tube 1. So we're going to use our dropper to take a little bit of our solution and pour it into our test tube 1. Then we're going to use another dropper to take our acetic acid and pour it into our test tube 2 using our dropper. Take note that we are using another dropper. And lastly, we are going to pour our hydrochloric acid into a beaker. And pour it into test tube 3 for we're only going to pour a little bit. Then we're going to use our hibiscus flower indicator to check or test if it's the testing, where we have our 3 solutions. We have our ammonium hydroxide, which is a base, acetic acid, which is an acid, and HCl, which is also an acid. So I'm going to use a dropper to extract some of the indicator, and then we are going to pour it into our first test tube and see if it's really a base or an acid. And we're going to use our pH to see or check the color change and see if it's a weak base or a strong one. Using our pH, we can see that the color falls under it's 6 and 7, which means this is a acid. Then we're going to pour the second one into test tube 2. So in response to the color change, it falls between 1 and 3, meaning it's our acid. Because we should take note that if our pH is from 6.9 going to the level, which means reducing, it means that it's an acid. If it's 7, it's neutral, and it's from 7.1 going upwards or to the right, it's a base. So I'm going to check our last test tube. The pH is 1, which means this is an acid. So in conclusion, we can say that the indicator that we have made using hibiscus flower is potent, and I highly recommend using hibiscus flower to prepare your own acid and base indicator because it's much more affordable and cheaper.
To you all, my name is Kuraranazo and I'm here with my group members and we'll be doing the introduction of the microscope. First we have to understand that the microscope is a magnifying glass with a double convex lens used to see microorganisms that cannot be seen with the naked eye. It was first invented in 1590 by Dutch spectacle makers Hans and Zacharias Janssen, who created the first compound microscope, and the first single lens microscope was later developed by Antonie van Leeuwenhoek in the 1600s. How the microscope came about was through centuries of discoveries and advancement in optics and refinements of making lenses. And Antonie van Leeuwenhoek in the 1700s was credited for the first effective single lens microscope. First, we have to make sure that our microscope has a power source, and then we turn it on using our switch, where it will emit a light from the light source onto the diaphragm, reflecting onto the microorganism, which will be on the stage, which we have mounted. We can then use our coarse adjustment to adjust the stage up or down to see the microorganism more clearly. We also have our X-axis knob, which is used to adjust the slide forward and backwards for clarity as well as our Y-axis knob, which is used to adjust our slide left and right to see the microorganism more clearly. We then have our eyepiece where we look through in order to see our microorganism, which we see through our lenses, which we have to start on the 10x lens in order to find the filter where the specimen is. We can then turn our lenses as they are bound with our nose piece in order to see our organism, in order to intensify the clarity of our organism using our 4x lens, our 40x lens, our 100x lens. We then have to look through our eyepiece. Now we are using our x-axis now to bring our slide forward to see our microorganism as it was too far. Thank you.
Greetings to you all. My name is Nsawa Panda and here I am with So in our group we are going to be preparing the solution hydroxide, which is known as salt. So we are one of the group members in the science club in Bright Star High School. So Shumbeko will be doing the calculations of mass and Talo will be doing the practical presentation. So here we have the still water inside our wash bottle, and then here we have the volumetric flask. Here we have the sodium hydroxide, which is known as the salt, and then here we have the funnel, we have the stirring rod, we have the beaker, and then we have the spatula. So in the first method is the calculated mass of 5 grams of sodium hydroxide will be carefully weighed in a beaker using a weighing balance. So the first step is that Shumbeko will be doing the calculations of the mass.
Calculating mass of sodium hydroxide using a concentration of 0.5 moles and volume in liters or dm cube, which is 250 milliliters or 0.25 dm cube. So for calculating mass, we're going to use, first we need to calculate the molar mass of sodium hydroxide using the formula. The mass number of sodium is 23. We're going to calculate the molar mass of sodium hydroxide using the relative masses. The relative atomic mass of sodium is 23 multiplied by 1 plus 1. The relative atomic number of hydrogen times 1 plus the relative mass of oxygen, which is 16 times 1. Then we'll get 40 grams per mole. Using our formula to find the mass will be concentration multiplied by molar mass multiplied by volume. We substitute all our values into our equation. It will be 0.5 mole per dm cube times 40 grams per mole times 0.25 dm cube. Some of the values here will cancel each other out, which will be dm cube, mole and mole, leaving us with our unit grams, which will get 5 grams. Our sodium hydroxide using our electronic values.
After we have weighed the sodium hydroxide in a beaker using a weighing balance, small amount of distilled water will be added and the mixture will be stirred for sodium hydroxide to dissolve.
So first we need to add a little distilled water into our volumetric flask before we add our solute. Kindly pour this. And our fun. Now you need to stir. After it has all dissolved, we add it into our volumetric flask. We add more distilled water until we reach our mouth.
So the third step is that the solution will be transferred into a 250 centimeter cubed volumetric flask with the aid of funnel.
We already done that.
The fourth step is that the beaker and the glass rod will be washing with small amount of distilled water and all washing will be transferred back into the volumetric flask.
So we will quantitatively add to our volumetric flask as we wash it. Rinse again. Rinse again. Again. So now we keep it
Uniform mixing.
okay, we're mixing our solids. Until it reaches the required level. Mix.
The date is the 11th of November 2025.
Wet the paper. Then this experiment will be done.
Good day, ladies and gentlemen. Standing before you today is Leyland Mugeni, and I'm here with my group members, Shamaine Mukola, Shilubelo Mashamba, and Dianu Chawuke. We learn at Bright Star Christian High School, and we are part of the Science Club. Today we are going to present about simple titration or neutralization reaction. Firstly, what is simple titration? Simple titration, it is an experiment that we use to find the exact amount of an acid which reacts with a base. This helps us to know the total amount of an unknown solution using a solution of a known strength. Then, what is neutralization? Neutralization is a chemical reaction whereas an acid reacts with a base to form salt in water. We use this, it helps us to balance and neutralize a solution. So, today, these are the equipments that we're gonna use. Here we have a bread stand. Here we have a bread. This is a wash bottle, and this are conical flasks. We also have beakers, and we have a phenolphthalein indicator. This is a pipette session valve. This is a pipette, and this is a funnel. So from that, we also have two solutions that were prepared. The first one is hydrochloric acid, which we wrote A. Then our solution B is sodium hydroxide. So now we are going to going to mount the bread on the bread stand.